As you probably can guess from the title, this video is about identifying conic sections. So looking at equations like these, with the xy term, pay attention to that, and like being able to tell what type of conic section is this and is it degenerate. So I will just explain how to do that in this video. If you can already do it, you already know it. You can solve this question, then I just skip this, but if you can't, definitely it is worth watching this because this is important, and you don't want to get to a test and this is a free question if you know how to do it. It's not hard at all. It's very simple, very quick, and just I think it's very important to know, and it's common to see it, especially on mu alpha theta tests. As you can see, these are from mu alpha theta tests. Okay, so I'll just get straight into it. First, it's always good to identify whether the equation is degenerate, because there's no point knowing whether it's an ellipse or parabola or hyperbola if it's just degenerate anyways. Like if it asks you what conic is described, you want to see if it's degenerate first, right? So here. Oops. So first, let's look at question 10, actually. And the way you find whether a conic is degenerate is whether the matrix that you can form with its coefficients, whether the determinant of that is 0. And that's not too bad to remember. The matrix is a little weird, but it's not too bad. And what's interesting is that most of the times when a system of equations is degenerate or like something else, just when you look at Cramer's rule, it's degenerate if the original system is, the determinant is 0, right? And in a lot of instances, stuff is degenerate or doesn't work, like with the eigenvalues, if the determinant of the matrix is 0. And I don't know why, but I do think that's very interesting. Oops, not ECF. I do think that's very interesting, and I think it makes sense. But I feel like that's definitely something, if you're interested in, you should look into. I've tried. I haven't really found any good resources, but if you do, you should let me know because that is very interesting. Anyways, this is a matrix you have to make with the coefficients of your equation, and you might be like, "Wow, how the heck am I supposed to remember that?" But it's really not bad at all. The way I always do it is, if you saw me do it, is I write A CF on the main diagonal. So that's the coefficient of the x squared term, the coefficient of the y squared term, and the coefficient of the constant term. And actually, let me write the original equation up here. Plus bxy plus cy squared plus dx plus ey plus f equals 0, right? This is, if you remember, general form. So luckily, all of these equations are in general form, as you most likely will see. And then you just take the a, the c, and the f, so x squared, y squared, and constant, put them on the main diagonal, and the rest of the values you just divide by 2 and fill in. So I think of it as like b fills in the space between a and c, and then you just keep going, right? As you expand out, you go from b to d to e, fills in the space between c and f, and it's not too bad to remember. I feel like at least it's not random stuff everywhere. And the most we do with our coefficients is divide them by 2. So it's not too bad. And so if this determinant is equal to 0, well, then our conic is degenerate. So without the basic proof, that is just what happens. I'm sorry, I cannot explain why. So yeah, let's set up this matrix. So first, for this question, we have to figure out which conic, right? We have to try, if you were doing this question in real life, you'd probably have to try all 4, except you can eliminate a few. Like, for example, B. B is xy equals 1. So I really, this is a pretty common hyperbola, and it looks like this, where the vertices are at 1, 1, and -1, -1, and they get closer and closer to the axes. It's just a hyperbola that looks like that. So we know that, hopefully you know that. You should probably know some common conics, and that is a very common conic. So that's not an option. C is one that you could also eliminate. Like if I were looking at this, I could eliminate it. And I guess once you start looking at these more and doing more of these, it just becomes easier. The thing with C is that x squared plus xy, well, x squared plus y squared equals 1. That's a circle, right, of radius 1. And so the xy term, it adds rotation. But you can't rotate a circle. When you add an xy term to a circle, like, that just doesn't work, because when you rotate a circle, it's still a circle. So when you add the xy term, it actually distorts it a bit, and it makes it into an ellipse. And I just know because I've seen this before. I wouldn't say it's a common conic section, but you will see it, like, it's not uncommon. So that's why you can eliminate C. And so that leaves us with A and D. And I didn't want to spend even longer on this video, so I'm just going to tell you the degenerate conic is D. But let's see, okay? Let's solve this out, and I will show you, that it is D, and that the matrix determinant is 0, rather than just being like, oh, it's D, right? So we're just going to say A, the coefficient of the x squared term, is 1. B is 3, so we're going to write 3 halves here, 3 halves. C is 2. D is 1, so we're going to write 1 half. 1 half. Oh, actually, no, it's not. Because there is no x term, right? I went straight to the y term. Just be careful about that. I am guilty of making those mistakes a lot, clearly. So there's no x term, but the y term is 1, so that's E. So we have 1 over 2 here, 1 over 2, and the constant term is -1. So that's what we're going to write here. And here's our matrix. So now all we have to do is solve it for the determinant. I said that weird, the determinant, but yeah, the determinant. And it's nice that one of these terms is 0 because it helps solve this faster. So let's go down the first column, and we get that the determinant is 1 times, and the submatrix of 2, -1, 1 half, 1 half, minus, because remember we alternate signs, 3 halves times the sub or minor matrix of 3 halves, -1, 0, 1 half. Remember, we get these minor matrices by just bloop, bloop, crossing out the row in the column that our term is in, and it leaves us with the submatrix. And then we don't have to worry about 0, since anything we multiply 0 by is just going to be 0. So let's multiply these out. We take this, multiply those two, subtract the product of those two for our determinants, and you get 1 times 2 times -1 minus 1 half times 1 half minus 3 halves times the product of 3 halves and -1 minus 0. Okay, that's really nice. So this ends up being 1 times 2, well, -2 minus 1/4. So that's what, -9/4 minus 3 halves times -3 halves. So this becomes -9/4 plus 9/4, which is 0. What? Who would have guessed? It's not like I already told you it was going to be 0 or anything. But yeah, so as you can see, this is 0, and that means that conic is degenerate. Okay, so now we look at 5, and we have to look at what conic section is described by the equation blah 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 blah. So first, whenever I see a question like this, well, in this case, this is why wording is really important in math tests, especially in certain math tests. Like, you always have to be sure that you read the question multiple times. Like, in this case, I probably would feel safe, like, not even solving to see if it was degenerate or not. Because, like, it says which conic section, and technically, I like, for example, a degenerate parabola, you can argue that it's still a parabola, but sometimes they'll say, like, a degenerate hyperbola, if it's just 2 parallel lines, it's not a hyperbola. So it really just depends on wording. If you said that this was, like, for example, a hyperbola, and it ends up being a degenerate hyperbola, you could probably still argue that it is a hyperbola, and you could dispute it. But generally, they'll say, like, which non-degenerate conic section. So you want to make sure that you solve first that the conic is, in fact, degenerate. It's not degenerate. So let me copy this and bring it down here. Bruh. Really? Oh, there we go. Okay, so let's first, just for fun, so you can see that, you know, this is the discriminant determinant, sorry, isn't always going to be 0. Let's just solve, it'll give us nice practice. Let's solve for the determinant. Yeah, I always get determinant and discriminant mixed up. But if you don't want to see this, fast forward, okay? But if you want extra practice in this, then, you know, watch it. Do it with me. So we have the A term, we have the B over 2, which is 4 over 2, which is 2. Our C term is 1. Our D term is -6, so this is -3, -3. Our E term is -6 as well, so you get -3, -3, and our F term is 7. So when we take the determinant, we get 3 times 7 minus -9, minus 9 actually, so we get 3 times -2. We alternate signs to get -2 times 14 minus 9 again, so 5, and then plus -3, so just -3 times 2 times -3, which is -6, minus -3. So -6 plus 3, which is -3, and I kind of did that fast, but hopefully this is right. So you get -6 minus 10 plus 9 equals -7. So as you can see, that is not 0. Hopefully I didn't do that wrong, but I probably did, which would be really embarrassing. But even if I did it wrong, and the actual determinant is something else, it still won't be 0. I promise you it won't be 0. This is non-degenerate. So anyways, we know that it's oh my god, I can't talk. We know it's a degenerate conic, okay? So degenerate conic. Yay! It's not just a point or 2 lines or 1 line or whatever degenerate hyperbolas are. You should probably know the degenerate forms of all conics, but it is degenerate. Okay, that's great. Now for the easy, fun part. This is actually really cool. And I should probably look up why this works too. Or you should, or someone should. Like, make an easy proof, because whenever you get into analytic geometry and stuff like that, the proofs are always so complicated for no reason. Like, just make it simple, easy. Okay, that was a joke, obviously. But yeah, anyways, so the way you find what conic it is once you identify that it's not degenerate is b squared minus 4ac. Where have we seen this before? Oh, that's right, the quadratic formula. Oh, that's right, also the area formula for ellipses. If you don't remember, that's 2 pi I over 1 over f times b squared minus 4ac. So this is very, 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 very common, you know, which is pretty cool. So this is what we use, and remember, we use the same a, b, c as our coefficients, the first 3. So if b squared minus 4ac, if it's less than 0, then it's an ellipse or a circle. You know, it's just, you know, it's an ellipse, but a circle is a type of ellipse. The way you know it's a circle is if A is equal to C, then it's a circle, which makes sense, right? Equal coefficients for the x squared and the y term. Okay, unless there's an xy term, okay, then it's not a circle, then it's an ellipse. And then if we have that it's equal to 0, b squared minus 4ac, then it is a parabola. And if it's greater than 0, there's really only one left, right? But it's a hyperbola. And you know, a funny thing, then it's a hyperbola. So it just blows my mind how simple this is. So when we do b squared minus 4ac, we have 4 squared minus 4, because, you know, b is 4, a is 3, c is 1. We have b squared minus 4 times 3 times 1. And, you know, I know this is a really hard thing to do. This is really hard math. But just stay with me for a few seconds more. We get 16 minus 4 times 3 times 1. which is 12 times 1, which is 12. 16 minus 12, if you can't do this, you can count on your fingers, is equal to 4. And 4 and 0, which one is bigger? 4 is greater than 0, right? The little greater than symbol, the alligator mouth is chomping the 4 because it's bigger. I don't know if anyone learned that. Okay, I should probably shut up and just move on with this question. Well, 4 is greater than 0, which means, ta-da, it's a hyperbola. It is a non-degenerate hyperbola. Yay, isn't that exciting? The answer to this question is D. I hope this helped you. I should stop talking now. Bye.